Let us now discuss one more special function. It is more of its use is more of technical nature, and it's very convenient for calculation of some definite integral, especially trigonometric ones. So, and this is called Euler integral of the first kind, or beta function. So the general notation is b is a function of two parameters, and the very first definition is according to the following formula. And of course, a simple convergence analysis indicates that this definition is valid only for the case when the real part of m and the real part of n is larger than 0. Only if this condition is fulfilled, the integral is convergent. So let us see on some specific example why this definition is of particular importance. So let us start from some motivationary exercise. So let us, for example, try to evaluate the following integral. The first step in evaluation of this integral is almost obvious. We would like to change to get rid of trigonometric functions, and say the most convenient way to do this is to introduce a substitute. Sine squared x equals u. Then a set of useful identities is as follows. And in writing all these equations, we made use of the fact that angle of this sine belongs to the range between 0 and pi over 2, so both sine and cosine are positive. So with this in mind, we can rewrite the integral as follows. So the integration goes from 0 to 1 du over 2 square root of u square root of 1 minus u, and the rest comes from this u to power nu over 2. So the next step is almost trivial, is to reduce this integral to the form of the Euler integral, so that it becomes 1/2 integral between 0 and 1 of the following expression. And immediately from the definition, we may read the following result. So as expected, as promised, actually, so we can write this integral in terms of this beta function, and it becomes beta of a beta of nu over 2 plus 1/2 and 1/2. So with this, motivated by this example, and actually in your homework exercises, you will find some more examples of how trigonometric integrals are reduced to beta function. Let us now try to understand the properties of this function. So first, actually, we will prove in this lecture the following very useful identity: that beta function of two arguments can actually be factorized to the following fraction. Where gamma capital is just Euler gamma function, well familiar to you. And notice also that beyond simply additional way to calculate this integral for real parts of m and n larger than 0, it actually, this right hand side actually provides an analytical continuation of this function into almost a whole complex plane beyond, of course, poles of the gamma functions in the numerator and zeros of the gamma function in the denominator. So with this in mind, we will now be concentrated on proof of this very useful identity. But now imagine that we are equipped with this result, then we can actually simplify our trigonometric integral even more. It's 1/2 gamma function of, here comes gamma function of 1/2, which is just square root of pi. So Okay, the rest is the most interesting part of this lecture, and now we are going to prove this very well-known formula. So let us see. Let's recall what are our basic definitions and what is the statement which we're going to prove. So we have two definitions for gamma. First one is for gamma function, and the second one is for beta function, which is function of two arguments. And we are going to prove a remarkable identity. And in discussing this proof, you will see a very useful trick, which will be definitely useful for evaluation of other definite integrals. So make yourself ready to realize and memorize it. So the trick goes as follows. So now we are going to evaluate a product of two definite integrals by reducing it to another definite integral with a carefully chosen change of the integration variables. And then after this change, the integration can be explicitly performed. So it's very convenient to do this. And we'll start, in a certain sense, from the result. Let us try to rewrite the right-hand side, the part of the right-hand side explicitly. So the product of two gamma functions is a product of two definite integrals. And the first step is very simple. So we find it convenient to introduce, instead of x and y, new variables, which are just old variables squared. So that the first step goes as follows. And the integration domain is, of course, still from 0 to plus infinity. So first of all, the exponents combine into something quite familiar and convenient. This is just product of two exponents. So next, let's see what else do we have. We have dx and dy measure, which becomes du dv, and the rest is 2u times 2v. And this is just a part of the change of the integration measure. So we have dealt with that, this, and this. So, and the rest, what we have is x and y to certain powers, which is just times v. Okay, now what is useful in this expression is that we have sum of squares in the exponent. This sum of squares seduces us to introduce a new set of variables, that is to go to the polar coordinates. So in other words, what we say is that u and y are just Cartesian components of the polar vector. And from integration over u and y, we go to integration over rho and phi. And in doing so, we need to be careful about the integration domain. And let us draw here, as a side note, the integration domain for variables u and y, u and v. And notice that we integrated only, so this is a plane of real u and real v. And in our left-hand side in this expression, we integrate only over 1/4 of the whole plane of u and y, u and v. And of course, it means that after going to polar coordinates, our polar angle will be restricted to an interval between 0 and pi over 2. So let's proceed. And conveniently, this du and dv, as another side note here, du and dv is just nothing but area measure on this plane. And in the polar coordinates, this is just rho times d rho times d phi. So having this in mind, we just write down integral from 0 to infinity rho times d rho, then integral from 0 to pi over 2 d phi, and this is just these two factors which I just measure. Then we have 4 times this UV and some certain powers of U and V will be presented in the next step. Now this is nothing but rho squared. Сейчас небольшая пауза. Кажется, я собираюсь чихнуть сейчас. Секунду.
Давай не на доску только.
Само собой. А тебе уж тем более не достанется.
Не, я имею в виду, чтобы
Не, передумал. Продолжаем. And the rest is rho cosine phi to the power 2m minus 1 and rho sine phi to the power 2n minus 1. So now everything is present here. So actually, interestingly, part of this integral can be evaluated explicitly, and in fact, after this change of the variable, integral again factorizes into product of two independent integrals. So this is the trick, the most important trick. So we had a product of integrals. Then after a change of the variables, it became some integral over the plane. And now after we switch it to polar coordinates, the integrals again factorize into integral over rho and integral over phi. And this trick actually does the whole job here. So first let us consider integral over rho. This is this factor, and finally rho to the power so this is everything which is about rho integration. Now comes phi integration. So next step is to perform this integral explicitly, and it's relatively straightforward. And by introducing new variable rho squared equal to t, we immediately realize that this is nothing but integral from 0 to infinity and this is exactly just 1/2 of the gamma function. And and we are left with the remaining integration over phi. And this actually, after change of after the change of variable, which is already familiar to you, that is introducing cosine squared phi equal to u, we realize that this is actually nothing but 2 times beta of m and n. And combining all this together, this factor of 2 cancels, and this becomes nothing but b times m and n times gamma function of m plus n. So, and this concludes our proof. So, as you have already seen how this familiar identity can be applied for definite integrals, especially trigonometric ones, you will have a chance to exercise in your homework, and during our course we will make use of this identity many times.